Oh, thank you, Ethan. I hope it won't be as bitter an end as you mentioned it to be. So it's been a really big pleasure to be back in Trento after all this mess of the last 2.5 years. And I remember really nice meetings having had here. And this just adds to it. And if it didn't get better with the hot weather. So many of you who know me associate me rather with a different kind of physics than I'm talking about here today, but I noticed that there are some overlaps. So my background is from electron scattering, and I'm engaged with the MUSE experiment with some of us here. And previously I worked on Olympus at DESY on two-photon exchange. So all of these things have radiation in common. And these kaon decays that I'm going to talk about has been my second pillar to build my academic career on with a program in Japan using stopped kaons and looking for kaon decay modes. And there's one particular one that we obtained a recent result for the radiative K plus decays into leptons and a photon. Has obviously some overlap with what is being discussed here. So I felt I should report. Does this advance? Okay, yeah. So the TRACK program. TRACK is an acronym that stands for Time Reversal Experiment with Kaons, so looking for time reversal violation. That was an early proposal when JPARC was founded around 2005, 2006. This program never really happened, but as the years went by about 2010, the focus shifted on lepton universality and the question whether the lepton couplings are the same for E, mu, and tau. And lately, this has become a much more prominent topic with the data coming out of CERN. So around 2010, we found that with the limited intensity that is still available at JPARC in the early years, we could actually still do something meaningful with the apparatus and go for a precision test of lepton universality and at the same time also cover some byproduct physics such as searches for light bosons. So I'm going to show you a little bit more about the whole program and we'll end up with showing you some first results and the current status and how it's continuing. So here's the two proposals. One was the time reversal experiment with kaons that would have used the K-mu3 decay mode and looked for a time reversal odd observable doing a spin momentum correlation. And this transverse muon polarization would have been T odd, and any signal beyond the standard model and which the prediction of the standard model for that observable would have been very small. So that would have been a very clean approach to search for new physics. This would be mostly in the Higgs sector. But it required beam powers in beyond 100 kilowatts that are still not available at JPARC even 15 years into the game. So around 2010, this E36 proposal was conceived, and at the time it was also motivated to search for heavy sterile neutrinos. But the main part is to look for lepton universality, in particular in this very simple semi-leptonic mode ratio of kaons decaying into positron versus kaons decaying into muons with neutrinos. So that got approved within a year or two, and we pushed on to make this happen. This could live with the limited 50 kilowatt beam power at the time. So the timeline was that up until 2014, we would then start building the experiment. And in the course of 2015, we actually ran it at the end of 2015. And the analysis has taken quite a while, as we noticed that were more not so simple aspects to tackle, and therefore it took several years. And partially it was also due to the limited manpower, so you have to then stretch the time if you have not enough people. So we are now just getting the first results out. So about lepton universality, in the standard model, leptons are universal, and the charged leptons only differ by their masses, but have the same gauge couplings. And this has been tested extensively over the years, and it is typically good to the 0.1% to 1% level established in terms of various ratios of branching ratios. With a few exceptions where the couplings may not be so universal, and these are all dated from recent years, and it started here in this sector, but you see some 2 to 3 sigma deviations, and probably the most prominent and well-known ones are the most recent LHCb results, which are at the 3 sigma level. The G-2 discrepancy now found at Fermilab, again, added to the BNL result, giving a beyond 4 sigma standard deviation. If you consider that to be a feature of non-universality as well, in that the muon behaves differently from the electron, where there's no G-2 deviation. And the proton radius puzzle, which has some aspect of lepton non-universality as well, because it is still mainly the discrepancy between the muonic hydrogen result of the radius versus that of electron scattering or spectroscopy. And at the time when it was proclaimed, it was at the 5 to 7 sigma level, and maybe it's going away, but maybe it's just washing out. But there are some issues, as it seems, and giving good motivation to run more precision tests. So in case of the kaon semi-leptonic decay, so some people say leptonic, but the proper name is probably semi-leptonic, because you have the hadron that decays and you have leptonic final states. So the most simple two-body decay can be described in the standard model and using the structure term and some couplings and mass terms. And then you get that lepton pair. And so this has hadronic uncertainty, but if you take the ratio between two-body modes, going to E, going to mu, there are certain cancellations happening. And what one is left with for the so-called famous R sub K ratio is just an expression that involves mass terms. And this is an order of magnitude of the level 10 to the minus fifth. So one calls that also helicity suppression, because the electron mass is so much smaller than the muon mass. And some radiative correction terms, which is at the few percent level. So this can be described in the standard model very precisely. And the value is listed down here with a small radiative correction. And the precision quoted for this is really at the sub 0.1% level, or less than half of that. So any measurement of RK at that precision level, the calculation is super precise, but it's similar like in G-2. If the theory describes it precisely, you can aim at measuring it as precisely as possible. And if any deviation occurs, then this could be an indication for something that has not been accounted for in the theory. That is beyond the standard model then. So here's the experimental status of RK. Standard model value up here, you see this in the minus fifths. There were basically two measurements, one with Chloe some years ago, which has this value, and a more precise measurement with Na62 or Na48-2 it was, which is now Na62, giving this value. And they're shown here. They're consistent with the standard model value, okay? And the precision level is about 0.5%. If you combine them, 0.4%. And the Na62 method is based on in-flight kaon decays. So these kaon beams have high energy. And the motivation to run the Drake/E36 experiment was in particular by using stopped kaons as a completely diagonal method with different systematics, maybe not the same or not that order of magnitude better precision, but completely diagonal systematics, just to cross-check what's going on, and the precision level aimed at would cut it in half. Excuse me. Okay, so that was all motivation. The byproduct physics is mostly related to dark photon searches, or more generally the light neutral bosons. Dark photons would have universal coupling. There's some motivation for searching for them. They were a candidate to even explain G-2. But beyond that, there were anomalies like the famous beryllium-8 anomaly, or the proton radius puzzle that can also explain with non-universal new physics involving light neutral bosons that would have some selective coupling beyond universality. And in the TREC E36 experiment, there were several decay modes that one can explore here. Here, for example, the muonic mode, where an additional dark photon or light boson would be produced in the final state, as well as the pionic mode, where you can produce this in the final state. And these analyses are still going on. So this program happened at JPARC. Where's JPARC? JPARC is in Japan. So I've always loved to go to Japan. JPARC is located in Tokai. That's about 200 kilometers northeast of Tokyo on the Pacific coast. Here you see an aerial view from rather the early times. There's also a monastery with monks that have to cross over here. There's a sandy path to the beach because they need to go at 6 a.m. and greet the sun. But apparently there's an accelerator facility in the way now, but they found a way. Okay, here's a schematic view of the hadronic facility, which was the one on the bottom right here. So that's the several stages of synchrotrons. There's an up to 50 GeV, 30 GeV in our case, that is extracted into this hadron hall. And this hadron hall then has various, it has a main production target and then various secondary beam lines. And you see a double C structure here for the low energy kaon beam line where our experiment was hosted. A top view of this, so the beam comes in from the left, produces secondaries, Ks, Ps, that are then selected. There was an electrostatic separator to then also have pi and K separation. And at the end of this channel, the TREC experiment would be set up. The rates, well, the times when this was constructed, that's more than a decade ago, there were some setbacks. Some of you might remember there was the big 3/11 earthquake of the northeastern Japan that caused some damages, but recovery went rather quickly. But then there was also a target incident with the primary production target, which had partially molten and contaminated the local area, including the exterior. So that caused a big hiccup and delay. And it took over a year until the management implemented safety measures that would address all these possibilities that can arise. And it slowed down the program, but we were then one of the first experiments that used the beam again. And that was started at the end of 2014, beginning of 2015, we had the first commissioning beam, and the experiment was then run in the course of 15 until the end of 15. But then the experiment had to be removed because this whole beam line in the red box had to be removed because they were building a new high momentum beam line for the then this designated flagship experiment of COMET. So we had a very tight time window to do anything at JPARC. The rates were as listed here. You have some 200 kilohertz of kaon flux, and the improvement of this facility compared to what was done at KEK some 15 years earlier is that the pi to k ratio was of order 1. And that's a significant achievement to do in order to be able to do kaon physics. So the TREC apparatus, it's shown here schematically to begin with. I will have some pictures later, but it's a toroidal spectrometer to begin with. Looks like an armrest watch. So you have 12 sectors. These are magnets with iron cores. So they are able to deflect the decay particle trajectories by 90 degrees. And in a side view of this, you see this depicted. So the beam would come in from the left. I have a bigger view of this. So the beam would come in from the left, be degraded, and then be stopped within an active target in the center of the setup. So inside this active target, the kaons stop. After a little while, they would then decay. And the decay products can be charged or neutral. The charged ones, at least those that are aligned with any of these 12 gaps of the spectrometer, right? They would be tracked with wire chambers before and after the magnetic field, so we can completely reconstruct the trajectories here. And then there's particle identification systems for the charged particles, as there are time of flight counters in the interior, aerogel Cherenkovs for E versus mu, as well as the time of flight method. And at the end of the channel, we have a lead glass counter to then still do again E versus mu. There are actually 3 PID systems to distinguish E and mu. And that's necessary, as I will argue. The whole setup is surrounded by an maybe 70% of 4 pi coverage, segmented cesium iodide, palliated cesium iodide calorimeter to detect neutral particles, photons in particular, but also leptons that can go in any direction that is not aligned with these gaps of the spectrometer gaps. So it has 12 holes, but otherwise it covers like a barrel the entire solid angle with holes at the entrance and exit as well. So this is basically the detector structure. So it has a lot of elements, complexity to it, and it's dense. Here's a picture how it really looked. So it has some resemblance. So you see the scale. This is Bishoy, and some of you remember him. He was my graduate student on the project in all these years. So you got the toroid here, a side view. The subsequent detectors can be moved back and forth and be close to the magnet. This houses the system of the lead glass and time of flight counters for the charged particles that make it through the spectrometer magnets. But then there's also this interior region where we have the inner detector with the photon colorimeter and the additional PID detectors. The target was built by Triumph. It's a 256 scintillating fiber bundle, 20 centimeters long, and read out with SiPMs. And the light would be guided with embedded wavelength shifting fibers. So there's a little groove carved into each of these bars. Each bar is 3 by 3 square millimeters. So that gave enough sufficient light output, and it would then be read out and digitized with flash ADC technology. You see some performance here. So the target is such that it's actually oriented longitudinally. That means the incoming kaon beam, it will eventually stop somewhere along the extension of the target, and it would populate only a few fibers and give a strong signal. So one can actually identify the XY position of the K-stop. That's how we refer to it. And then you wait for 10, 20 nanoseconds and look for the decay track. And if it's a charged lepton, you would see transverse traces of other fibers lighting up. These are the red dots here, forming a trajectory. This can be linked with the hits in the outer detectors, and you come up with hit patterns in the XY coordinate cut through the target. You see how the beam populates the transverse plane of the target. Surrounding the target was another tracking element of a spiraling fiber tracker, and with helicities in both ways. So we have crossed helicities of scintillating fibers. You see some pictures here that covered the entire length of the target and gave us an inner tracking point at the millimeter precision level. That was deemed to be sufficient for the purpose, because you have anyway a lot of multiple scattering inside the target. But that's basically all the track information you then have in the interior. That is then surrounded by aerogel, but then outside of that is the cesium iodide barrel. So here's a schematic view where you see the many crystals, 768, and with these muon or lepton holes that would then be aligned with the gaps of the 12-sector spectrometer. So this photon colorimeter, it was also built and used in a previous experiment, then based on pin diodes for the readout, which have a long dead time. And in order to make this higher rate capable, flash ADC technology was also deployed here, which allows a complete pulse shape digitalization and handling of pileup events like the one that you see here, which can be analyzed event by event and be unfolded from previous events that overlap. So this is allowed to crank up the otherwise very limited pin diode rate limit quite a bit. And so for the calibration, we're using prominent decay modes, such as, in this case, for the energy calibration of the crystals, we used the most prominent K plus to mu plus nu decay, which gives you a monochromatic muon of specific energy and nothing else. So that is a good channel. It can be identified easily. It's abundant. It's 64% of the branching of the decay width of the kaons. So you get many of them. And if it's muons, chances are that you populate only a single crystal from the segmentation of the colorimeter. And if you have single crystal events identified, this gives you then a peak. So this K mu2 peak, and that is the information how to calibrate the energy of each crystal, because you find this K mu2 peak, which is monochromatic in each of the crystal readouts. So then the spectrometer information had to be combined with the colorimeter, and there's another reaction that is very prominent. It's called K pi 2. That is when the K plus decays into pi plus and pi 0. So two pions, one is charged, one is neutral. The pi 0 would decay into two photons predominantly. So you get 3 particle events. But the momentum of the pi plus and of the pi 0, because the K plus is at rest, is again monochromatic. It's a constant value. So you can use this to verify what you're doing. So you see momentum information from tracking against time of flight reconstructed invariant mass here and some other parameters. And under that condition that you pre-select the pi pluses from K pi 2, you can then look for 2 cluster events where you detect the 2 photons from the pi 0 decay in the colorimeter and verify how good the energy calibration was from using the muon. Okay, so maybe I should move on and not be so technical here. The momentum is determined by tracking. As I said, we have the charged leptons that go through the magnetic field, which is being tracked before and after. So from 3 tracking planes plus additional target information, we can then reconstruct the momentum. And my previous postdoc, Tong Tong, has created a Kalman filter code that we actually also used in Muse to reconstruct the momentum at various places under accounting of energy loss effects. And you see the 2 prominent decay modes, K mu2, K pi 2, in the momentum spectrum of the charged lepton. Okay, we also put all of this in a simulation. So this was mostly Bishoy's PhD work. So you see the various elements that he produced in the Geon 4 and how it compares to reality. So he started this off actually 2 years earlier before he ever got to see this. But we have everything here. And what he also added was an extended generator class and connected this with Geon and Root. So we have various decay modes that can be dialed that have the branching ratios as posted in the PDG, but we can also do a biased simulation by assigning weight factors to select certain rare decay modes if we want to. And that includes then also the modes that we are mostly interested in. And this technique is being deployed in particular for the light boson searches where you do not know the branching ratio a priori. So about PID in this experiment. So remember, we want to measure RK, which is at the level of 10 to the minus fifth. And you want to measure this to better than 0.5%. That means the misidentification of mu into E, which is very likely to happen, but it should be suppressed at a level 10 to the minus 8. And with this technique alone, 10 to the minus 6 was designed to be suitable. Plus, we will have momentum information to separate the KE2 and KMPI2 in the momentum spectrum. But from the plain PID aspect, you want to be below the 10 to the minus 6 level for MIS-ID. And no single PID system can achieve this. So that's where the redundancy was put into place. So we have PID with time of flight, with aerogel, and with lead glass, all aimed at separating E from mu and to avoid confusing a muon for a positron. Okay, you see some performance here, and you see in the momentum versus detector response of the aerogel here and the lead glass here, and the time of flight mass reconstructed, you can identify the prominent decay modes just visibly. And you can identify where the events of interest would be situated. So KE2 would be in this red spot up here. There's always K mu2, which is really, really dominant. Even if you apply some PID cuts already, you only reduce it, but you will never suppress it entirely. There's KE3 down here at the lower momenta. So there's a momentum separation and a separation in the response of the three detection systems. So for the first results that were created, the technique deployed was to use an analysis of cut point dependence, which is then depicted here for each system. You can use samples of pure, in quotation, species by selecting cuts on any two systems in order to characterize the third system. So that's how the efficiency curves and rejection probability curves were obtained as a function of the cut point of that third system. And then the black line identifies the work point that was then selected for an optimized analysis. All right, so now for the extraction of some physics here. So there's a little story to the KE2 gamma channel. So, I try to illustrate this on this slide. We want to measure KE2 over K mu2, but whenever you measure positrons, there's also radiation. There's internal Bremsstrahlung, but in case of kaon decays, there's also a photon emission due to what's called structure-dependent decay. So that's called KE2 gamma SD. Yeah? So it's an emission of a photon that is structure-dependent. It comes directly from the decay vertex, whereas the internal Brems would come from the outgoing lepton, basically. And these two types of photon emissions have to be handled separately. So in fact, the SD channel is the really explicit photon production, structure dependent, and it has to be subtracted from any yield that is found by detecting the positrons. So it's actually a background for the purpose of measuring RK. So we need to determine or estimate this background and remove it. In TRACK E36, we're actually able to measure KE2 gamma SD because we have this segmented calorimeter that gives us angular information and energy information. And you see how the structure-dependent photons separate from the internal Bremsstrahl photons. Well, they partially overlap in the interior, but they are well separated. The internal Brems is predominantly soft, and it's also more aligned with the outgoing lepton. So this theta gamma is the photon angle relative to the lepton. Whereas the SD is more energetic and also more back-to-back relative to the outgoing lepton. So there's a way to distinguish this. And since we have a highly segmented calorimeter, if we analyze events that have a photon cluster detected, we will have a portion of SD in the yield that is seen. So the calorimeter, this is this group of events. One photon detected and the charged lepton detected is composed of all of these events in the box here, internal Brems as well as SD. But then for the case of KE2, where we measure only the charged lepton and take no information from the calorimeter, it contains the SD as a background, but we will use this measurement in order to address the amount of it. That was the design technique in order to clean this. But then you still need to account for the internal Brems. So some of the internal Brems photons will be detected in the 1 gamma events. So we see some of that as well. But we need to account for this yield and include it in what's then extracted as the branching ratio for KE2. All right. So the cesium iodide calibration also required considering accidentals, and at the level of some 20%, we found that there's the likelihood that there is an accidental cluster, so one has to deal with this combinatorics, and it was achieved by doing event mixing in a Monte Carloing technique, using a clean channel such as kpi2 and mixing this, using a clean channel, yes, and using the information from the kmu2, which does not necessarily come with a photon cluster, but 20% of the time it did, and we would mix this type of event with the detected event here in order to then describe the yield in full and come up with a calibration for how much accidental weight is included. In doing so, then we deployed another Monte Carloing or Monte Carlo based decomposition technique to then analyze the two types of events that I depicted. So the one on the right is where only the charged lepton is detected, whereas the one in the left and in the middle have either one or two clusters detected in the cesium iodide in addition. And then you see the decomposition curves, which are Monte Carlo generator based yields and with prominent shapes that are characteristic for the processes. So they're depicted in the box here. So the blue distribution is what we're actually interested in. That is the KE2 distribution, which is monochromatic ideally, but it's broadened because of energy loss and multiple scattering and radiation. So that is the blue shape of the histogram generated by Monte Carlo versus the green. The green is the SD background that I mentioned, which is contributing to the charged lepton spectrum. So one needs to decompose the blue versus green in order to reproduce with the red histogram the observed yield. But the portion of the green is constrained by looking at one cluster and two cluster events, which are then predominantly due to the SD process. So the red and green are almost identical in describing the data here. So most of the yield observed in the one photon and two photon events are actually SD events. The IB is suppressed here very much because of kinematic selections. And you have also one little contribution in magenta here, which is the unsuppressed yield from KMU2. We have applied already PID cuts and everything. There should be no muons, but still there are some, and how many there are is being evaluated in this Monte Carlo decomposition. So in doing so and varying the cuts and optimizing the analysis and doing the best we can, this then allows you to obtain, in the bottom line here, a ratio between the SD mode, so that's the amount of green, divided by KE2, that's the amount of blue, with a constrained fit of the three histograms. And we see that this ratio of branching ratios has a value of 1.12 with some 5% level errors. It's of order 1, one should say. And this is maybe worth mentioning that the production of photons is not helicity suppressed relative to the primary process of KE2. KE2 is helicity suppressed, that has a 10 to the minus fifth level branching ratio, but the SD channel has an equal order of magnitude branching ratio. And it is the background that has to be, it's significant in the yield that is otherwise observed. It is important to know this number for SD because our colleagues from the other experiments need to use it too. The Chloe experiment actually measured this as well. They were able to determine this, but the NA62 experiment at CERN had to use input from outside and run a Monte Carlo based background subtraction. So they would use the SD yield obtained from Chloe. All right, here's the systematics. I don't want to go into details. This has been largely optimized. It's all at the 5% level. But now let's compare the number that we found with the Chloe result that was measured previously. So we had to do a little bit of adjustment in order to make it comparable. So the observable that we measured is based on detecting E, numerator and denominator here, and separating SD over everything else. Okay, that's this ratio. Now, if you want to evaluate the Ke2 gamma over K mu2, which is the observable that Chloe actually reported, you can rewrite this as our ratio times R sub K. So this is how the two observables are related. So our ratio times RK would be the Chloe ratio, and the Chloe ratio would also be evaluated with the of momentum for the lepton more than 200 and photon energies above a certain threshold. For now, the numbers that can be compared. So if we convert our ratio into R sub gamma, defined that way, we would get a number, 1.85. And you see the order of magnitude is now 10 to the minus fifth because it's multiplied with RK. The Chloe number was at the level 1.5. And with the error bars, that's about thank you. With the error bars, that's about a 3 sigma discrepancy between the two measurements. So our value or our SD value differs from that of Chloe by 3 sigma. But it's being used, the Chloe value was used by NA62 to obtain their corrected RK result. Okay. We can also compare R sub gamma with theory. And some years ago, there was a chiral perturbation theory result offered, 30 years ago almost, consistent with the Chloe result. Okay. But now we are 3 sigma higher. There was also a lattice QCD calculation published last year, which is in agreement marginally with Chloe and in good agreement with us. So there's a caveat. So that is a bottom line here. We're in agreement with that is at the 1 sigma level with CHPT, the 3 sigma level. The caveat is we had to account for the internal Bremsstrahlung in the denominator here. If you look up here, the photon in the bracket means that you have the possibility to radiate an internal Bremsstrahl photon, and you have to account for any acceptance loss if the photon energy becomes too big to be outside of the detected interval. Then this affects the acceptance of the reaction, and it affects the branching ratio value. We had to include this in our simulation, and we did. And the effect was that the number actually decreased for the ratio by some maybe 7–8%. And before we did that, the discrepancy was actually bigger. Yeah? So accounting for the internal Bremsstrahl effect in the Ke2 process brought our result closer to that of Chloe and that of the theories. But there's a caveat, because one should also do this for the process in the numerator, for the SD process. So now it does, now it forwards. Okay. So in the first analysis that we published, it was only applied to Ke2, but not to Ke2 gamma SD. That would mean you have an extra photon in addition to the positron, neutrino, and photon decay mode already, creating a 4-body decay. So this required an implementation, and we were actually recently following a prescription given by a paper by Gatti. So I don't know if people here in the room are familiar with this author and this paper. It is a paper that reported on radiative Monte Carlo generators for kaon decay modes, or maybe also other meson decays. It's listed here. And it has I think I have it here for an example. So you see the Bremsstrahl spectrum up to an endpoint here, and above a certain cutoff, one can tell how much of the Bremsstrahl yield would be integrated here. That's for an example spectrum, and the prescription allows to calculate the Bremsstrahl spectrum for just about any kaon decay mode involving charged particles in the final state. And the Gutti prescription was found to be suitable for Monte Carlo generators in that it provided us with a analytic expression for the differential decay width as depicted down here with some parameterization. This value B is dependent on the species of the lepton and so forth, and some other parameters. And it can all be analytically evaluated and then coded. It can be applied for both the two-body decays of the kaon as well as three-body or more-body decays of the kaon, as long as you're interested in an extra Bremsstrahl photon. So that's a neat way of handling it, but I have no feeling for how accurate this actually is, or how to assign an error to that method. But it does work with the Monte Carlo channels, and we recently achieved an implementation of that, and the results are shown on this slide. So now we include the internal Bremsstrahl effect in the generator of the SD events as well, and this has moved our value from 1.12 to the values that you see down here. Actually, in this most recent analysis, we have an extra photon detector evaluated as well that I didn't quite talk about here, but there were also photon detectors that covered the solid angle of the charged lepton gaps that are not covered by the cesium iodide. And we carried out 2 independent analyses of these 2 types of event classes with photon detected. And you see the values are 1.25, 1.19 with errors for a combined value of 1.2. Okay, 1.2 to be compared with 1.12. So that move up by some 6% is due to accounting for the radiation in the SD mode that basically reduces the acceptance of SD and increases the branching ratio for the numerator term of our ratio. So that means in consequence that we're still consistent with lattice at the 1 sigma level, but the disagreement with Chloe as well as with the chiral perturbation theory has now increased a little bit from 3 sigma to 4 sigma, where sigma is the level of 5%, the quality of our measurement. So this is a preliminary result still, we're still debating it. So that's why I've tagged it preliminary, and it should be published shortly in the next few weeks or months. Okay, so I think that's what I wanted to mention here, and to address the Gutti scheme that has been deployed and whether there are some ideas to do it better or differently. And I'd like to come to my summary. So lepton universality is a quantity that's being challenged these days by various experiments, and perhaps they are the most significant hints for physics beyond the standard model. The E36 experiment aims to measure the RK ratio, Ke2 over K mu2. SD is a background of that and needs to be separately determined. We are almost there. And in addition, we will be able to say something about light neutral bosons also soon. We've been analyzing this for the past 6-7 years. I'm spending my Monday evenings on a weekly basis for about that time. And there might be T-violation opportunities in the future with the future proposed Hadron Hall extension, where another production target will be appended at the end of the Hadron Hall, and everything will be bigger, greater, more intense. But maybe I still, if I'm still active then. But it always takes some decades, right? Okay, so that's it for today. Thank you very much.